Everybody ready to say goodbye to our solar system? To our galaxy? Here we go.
Hello and welcome to every single sci-fi film ever. I'm Aisha Khan. Earlier this year, I contacted a brilliant scientist about whether they wanted to come on the show and talk about their favourite science fiction film. She responded by asking whether I want to learn about the science behind Interstellar. It's been 10 years since Interstellar was originally released on November the 6th, 2014, and is due to be re-released in cinemas on December the 6th, 2024. So I think it's a pretty good time to talk about Interstellar. I'm really excited to welcome Claudia de Rham onto the show. She is a theoretical physicist based at Imperial College London. Her work is at the interface of gravity, cosmology, and particle physics. She's also the author of the book, The Beauty of Falling, A Life in Pursuit of Gravity. Welcome to the show, Claudia. How are you doing?
I'm great, thank you. Thanks for hosting me. It's really great to be here.
Thank you so much for coming on the show. And let's start with, when did you first watch the film Interstellar and what kind of impact did it have on you?
Oh, wow. That's a great question. I think you mentioned we're going to celebrate its 10 years anniversary. So it was about 10 years ago. Not quite, maybe 9 months and 9 years and 10 months ago, something like that. The Science Museum in Cleveland, in Ohio, where I was living at the time, contacted me just before they released the movie. They were about to show the movie in a big IMAX theater, and they were asking me if I could come and give a little bit of a talk about the movie, which I was super excited to do. But I was 9 months and a few days pregnant at the time, so I just had to wait till
Wow.
till the baby came out.
That's very pregnant.
Yeah, I was very pregnant, and so I went first to watch it with my little one. She was with me. She was very cute. She would have been something like I don't know. I think probably 3 days old, 4 days old. I went with her. Oof. She was so sweet. And then, there is all of this. There's all these connections at so many levels between the daughter, also the mom and the father, and all of those dimensions in there, which are space-time dimensions.
Very much about, they're very much, although there's the whole scientific side of it, the emotional journey is very much about one man and his link to his daughter. Yeah, absolutely.
Absolutely. And then also to the future, the world you're going to leave to your daughter. So that was very much in my mind. It was very sweet. Of course, I was very focused in trying to understand physically what makes sense, what doesn't make sense. And she was helping me with that as well a little bit in this emotional journey. So it really stuck me. It was a very nice moment.
Okay, so let's just give a very quick overview. There are spoilers ahead for anyone who hasn't watched the film and just wants a quick overview. We are dealing with a bleak future in which growing crops has become quite a problem. Our main character, who is played by Matthew McConaughey, is a farmer, like pretty much everyone else on the planet is suggested. And it's almost like you have to become a farmer. You don't have the freedom to become an artist or a scientist or anything else because the world desperately, desperately need crops. And so despite the situation, he gets himself into a predicament in which he is required to go through a wormhole that's been discovered on the far end of the galaxy and find a planet for humans to populate so that they have a future available to them. But the problem is the planets are all close to Gargantua, which is a supermassive black hole. There's a huge emotional element because it is very much to do with Cooper and his daughter Murphy, who is like young when he leaves, and she has what we think is a ghost in the room. But before we get to all of that kind of time-changing, time-travel-y stuff, they use a cliche in this film, which is used quite often, which is they fold a piece of paper and they put a pencil through it. And they're like, it's a wormhole.
I'll show you how it works. So they say you want to go from here to there. But it's too far, right? Mm-hmm. So a wormhole bends space like this. So you can take a shortcut through a higher dimension.
Now, the wormhole in this film has been placed there by advanced beings. Yes, come on, Claudia, you can do this.
I can do it. Yeah, a little bit like that.
Yeah. She's holding a piece of paper in front of me. So can you explain to me a little bit about this wormhole? It's used really often. What is a wormhole? How do we know about it? Does it definitely exist?
Not that I know.
Not this particular one, but generally.
That particular one. So, I mean, in principle, it doesn't need to be something so crazy. What they have in mind, really, in the movie, I think, is something we do consider. We do consider space-time to be foldable. Space-time is a fabric in itself. And so it doesn't need to be all straight and flat and boring as we picture it necessarily. It can actually have some folding to it. And it could be that some region in the universe where we are actually very close to other regions in the universe if we take a shortcut through this folding of space and space-time. So very much like if you think of a piece of paper, it's easier to think of having an extra dimension out there, an extra dimension of space out there. And so the universe in which we live, you can have two very distant galaxies, for instance. But actually, if you were to cut through the extra dimension and then connect those 2 points, they could be quite close together. So it is you should think of them as a shortcut, using the beauty, using the whole structure of space-time as a shortcut. So that in itself is not entirely crazy in principle as a concept. I mean, we do explore the idea that there could be wormholes out there. There are solutions of Einstein's theory of general relativity. And actually, the whole movie is very much based on all of those ideas of Einstein's theory of general relativity, which is a very profound theory, and a lot of the notions that are being exposed are actually real things that we do explore. Okay,
and so we know. So Christopher Nolan, the director of this film, had Kip Thorne hired as he's an American theoretical physicist, and he was hired as a consultant throughout this film. And apparently there was a lot of back and forth between Kip Thorne and Christopher Nolan coming up with ideas for the script, and then Kip Thorne being told to go away and make the science work, which is why apparently a lot of the science in this is very, very accurate. So if something didn't work, either Kip Thorne would have to have an amazing brainwave and make something work, or he'd have to go back and say, sorry, Christopher, this really isn't going to work. But can you explain a bit about, so there's so many different terms used in this, but it says, one of the things was like, we are detecting a gravitational anomaly. Please tell me, Claudia, what's a gravitational anomaly?
So they're a little bit vague about that. I think what they mean with that is that there is a deformation in space-time. Precisely how they observe it, it could be through gravitational waves, possibly. It could be through a gravitational attraction around there. I think that's probably what they mean. Honestly, they're quite vague about it, but if you wanted to take a step back and think scientifically, what is happening in the remit of the movie, there seems to be all of a sudden a wormhole that has been created in the solar system, actually near Jupiter, as a way to shortcut us to another region in the universe where there could possibly be other habitable planets. I think that's
Now, in theory, when you say a wormhole's appeared, now we are assuming that these beings are so advanced they know how to do that. Would we have any idea how to create a wormhole?
Yeah, so this is exactly one of the issues. It's for one thing for a wormhole to be there. It's another thing to make it appear. So the thing with creating a wormhole is that you really need to change the whole structure of space-time quite dramatically. So it's not something you can tweak at one point locally. So it's hard to imagine how you would just make a wormhole appear without changing even the structure of the whole solar system quite dramatically along the way. So definitely there's those advanced beings that may be living in extra dimensions and having access to all sorts of other technologies. They must have access to quite a different type of even energy and matter than what we are used to. So how do we make space-time change and curve, we need to play with that space-time. And for that, we need to put some energy in it, or we need to put some pressure in it. We need to put in it some kind of matter that would affect the curvature of space-time in such a way that it wants to fold according to your will, or to the will of these super beings.
These bulk beings, which are from the future.
Beings, these bulk beings. So that in itself, it's a great idea. I mean, we do as theorists, or as people working in gravitational physics, we do explore the possibility of what kind of matter, what kind of stuff we would need to think of putting in our space-time so that it would lead to a wormhole, for instance. What we do know is this kind of matters, they are not stable matter. They have all sorts of pathologies associated with it that we wouldn't be able to control. So it would be very challenging to all of a sudden change the structure of space-time so that a wormhole simply appears.
Okay, very interesting. So should we move on to the general relativity stuff? Because there's a lot of stuff in here about time, and each planet has a different kind of time scale compared to Earth. So the first planet they go to is called Miller's planet, and the time difference there is every hour on Miller's planet is 7 years on Earth. Now, we get this in quite a few sci-fi films, but can you try and break that down? Explain like I'm 5, basically.
Yes. So first of all, that's science. It's it can't happen. What happens in that movie is that planet is very close to Gargantua, this huge black hole, and so if you are close to a very if you're in a very curved region of space-time, it is true that the way you experience the flow of time is different as compared to what we experience in a very flat region of the universe. It is true. It is absolutely true. We do know that. We do observe that. We do use that in our everyday life. That just for instance, us on Earth, we experience the flow of time slightly differently than satellites do on orbit above our heads, or astronauts in the International Space Station. They would experience the flow of time ever so slightly differently than us on Earth. An hour for them on the International Space Station is an hour minus a tiny little bit less for us on Earth, because we are in a more curved region. We're closer to the Earth, and so it's slightly more curved. We have a bit more gravitational attraction, if you want to. The gravitational attraction slows your clock down. That's the way you can think of it. So that
Very
difference, the difference between the astronauts and us on orbit around the Earth is present. It is something that we do account for when we're dealing with GPS satellites, for instance, but it's of the order of the microsecond. So every hour on the International Space Station, it's an hour minus something slightly, a few microseconds less for us on Earth.
Yeah, it's not very big, but I'm really surprised. I didn't realize that there was any difference between us and the space station. So
there is. And we do account for that with GPS satellites. We do account it because it is important in then determining our locations. So this is something that is not science fiction. It is technology, it is science, it is reality. Accounted for every second, we account for that. Now, when you're thinking of going somewhere else in the universe, if you imagine you're close to a black hole, like you do, if you're very close to a black hole, then you're in a much more curved, or the gravitational curvature is much stronger there than it is as compared to us on Earth. And so your clock over there would tick more slowly as compared to the way it ticks for us on Earth. So it is true that you can spend just a few seconds.
Would it be such a big difference? Like if there was a planet so close to a huge black hole, an hour equal to 7 years, that's completely reasonable within the theory of relativity?
That is completely reasonable, actually. Actually, if you're even closer to that black hole, you can imagine that an hour there could be infinite time for us on Earth. It could be the whole history of the Earth here on Earth. It depends how close you are to that black hole, actually. It's just about how close you are. As you go close enough to the black hole, time stays still. So you can spend just a fraction of a second, very, very close to the black hole, and the whole civilization of Earth would have gone through in that time period.
Now, this is in theory, because we don't recommend anyone actually going very near a black hole. Yes. There's a quote in the film which I just wanted to read out to you because I don't understand it at all. So it says, let me get it up here. Hold on. Time is relative, okay? It can stretch and it can squeeze, but it can't run backwards. With you so far on that. And then they say, it just can't. The only thing that can move across dimensions like time is gravity. Can you explain that, please?
So gravity can move across dimensions. That's absolutely true. It's not completely true that gravity can move back in time. That's not exactly true. What is true is that you can, through gravity, you can communicate across dimensions. But we have no reasons to believe, and actually there's no such thing in general relativity, where you could go backwards in time using gravity. I don't even know what it means exactly. Does it mean using gravitational waves? Does it mean something else? They're not very clear with that. Gravity, in some sense, is space and time, but it doesn't mean that you can use information from gravity to communicate backwards in time. That is, we have very strong reasons.
Well, that
to
is
believe
a large part of the film. So that bit is not science, is what you're saying.
That part is not science. That's where the transition to science fiction happens. That's right.
Yeah. Okay. And then when they return from Miller's planet, and Romilly's been on aboard the ship. He's been on board the ship, and he says, "I've learned what I can from the black hole." So that sounds like something potentially a scientist like yourself might really want to learn. What is it that we can learn from a black hole?
Okay, so we really want to understand gravity at a much deeper level. And we do, actually. There are lots of experiments, lots of observations are trying to understand very much by analyzing the behavior of gravity around the black hole, much more about how general relativity works, and if it matches with our expectations from general relativity. What they want really to know in the movie, I think, is the theory that goes beyond Einstein's theory of general relativity. And so we know if you enter a black hole, so as you're near a black hole, we can use Einstein's theory of general relativity to describe what happens. And everything so far is completely consistent. All the observations are completely consistent with what we'd expect and what we have probed. As we enter through the black hole, through the point of no return, even though in the movie the character returns, but
there is a return, yeah.
There's a return, but we would anticipate there to be a return. If you go through the point of no return, we can still use Einstein's theory of general relativity to describe what happens there. But as you go inside the black hole, closer and closer to the very center of the black hole, we know that there comes a point where Einstein's theory of general relativity breaks down, and there needs to be a new theory that takes over. So I think what they really mean in that movie is that they're trying to understand the underlying theory of everything that overcomes general relativity when general relativity breaks down at the very center of the black hole. So I think this oyster, the pearl of the oyster, is the singularity of the black hole. Yeah. That's almost the holy grail. They want to make it sound, and it is possible. It is like that if you understand how to describe the singularity of a black hole with exquisite precision, then we would have access to a theory of everything that encompasses everything that we know. It is a theory that from where even space and time emerge. So that would really be some knowledge beyond everything we have at the moment.
And when you say theory of everything, is that the same thing as the unifying theory, like between the very, very big and the very, very small? So
yes.
It's the same thing. So it's kind of like the holy grail of science.
That's right. That's right.
Okay. And when they go into Gargantua, now they say it apparently holds a chaotic singularity, but it also has two gentle singularities. Now, I just thought a singularity is a singularity and that's it. Can you explain what the potential differences are?
So I think what they mean there, I have to extrapolate a little bit what I think they mean. So there's different types of singularities. There are singularities like at the very center of the black hole, which is definitely a real physical singularity, and there we would need a new theory of gravity, a new theory of everything to describe what happens, and that's what they are after, I think. However, as you enter the black hole, they may seem like there's a singularity in the way you describe your physics as you go through. But it's not a real singularity. It's just the way we describe it. But we can describe it in a different way, which makes things much more concrete, and there's less issues with that. However, what is true is that typically when you enter through the black hole, you're going to be stretched along some of the direction and squeeze along some of the other direction to the point where we'll be completely pulled apart and no one would survive that. In any case, as I mentioned before, the clocks stop ticking as you go through the horizon of a black hole. So what they're trying to say in that movie, to make it interesting, is that those are soft singularities, so that if you go through them quickly enough, you're not going to experience any of the fatal consequences of what you would have expected. Yeah. So just take that as granted. Just because they need to make it interesting.
Yeah, and I think that a lot of the stuff that isn't science, they describe that as, so there's bulk beings, which are 5-dimensional beings, and they suggest that it's a future us or something. So everything that goes into the science fiction realm and leaves science, I think they're always like, yes, the bulk beings kind of did that in their, eternal futuristic wisdom. So I quite like the fact that they have that kind of get out clause. Okay. Can we talk about what on earth is a tesseract?
Yes. So interesting. Maybe the best way to think about it is to start with something simpler. Let me just think of a point. A point is something that has 0 dimension. Now I can make something which looks a bit like a point, but it's 1-dimensional, which is a circle. So it's something just along 1 dimension. I can only go along one direction in the circle. I just go round and round, or one way or another, but I have no other choice. It's one way or another along the circle. So the circle is 1-dimensional. I can think of something a bit more interesting, which is the surface of a sphere. So I bring the circle to an extra dimension, and that's the surface of the sphere. And I can go along two directions. It has 2 angles, and we can think of the surface of the Earth. Where you are on the surface of the Earth is described by the latitude and the longitude, for instance, and you can be on that surface. Now you can imagine moving that to 1 extra dimension, and you would have a 3-sphere. And you can imagine moving that to an even bigger dimension, and that would be a 4-sphere, being on the surface of a 4-sphere, where you would have 4 angles to describe where you are. What they have in mind there is almost the same thing, but with a cube. So you start with a square and then a cube, and then you want to think of this cube as having yet 1 extra dimension. That's what they have in mind.
Now, a lot of times people talk about time being the 4th dimension. Is that accurate or not?
So first, yes. So absolutely. We are thinking of space and time merged, wedded into one concept. And we do have lots of experiments that do show us how there is some rotation in space and time. What I experience as being some motion in space and some motion of time, you can experience as a slightly different motion in space and time. And so we really need to wed the notion of space and time together. So in our everyday life, we know we are living in 3 space dimensions, but time is the 4th dimension. That's right. But what they have in mind there is yet another space dimension. So the cube is in space and time.
So the tesseract, which is this kind of magical cube, which seems infinite to at least our 3D minds, is actually 4 spatial dimensions.
That's right. And possibly one of time. That it's hard for me to understand exactly what they have in mind, yeah.
You survived.
Somewhere in their 5th dimension, they saved us.
What the hell is they? And that's why they want to help us, huh?
I don't know, but they constructed this three-dimensional space inside their five-dimensional reality to allow you to understand it.
Hell, that ain't working.
So I'm just going to ask this because this is the bit where I feel like science fiction really takes off into the fiction direction. So when Cooper, the main character, is communicating through the second hand of the watch that he's left behind for his daughter in the past, is there science behind that, or is that just magic clock?
So what let me tell you what I think is scientific, or we can consider it as a science, is that they can be bulk beings. They can be in the fifth dimension of space. So we live in a 3+1 dimensional space-time, a 4-dimensional space-time, because it's 3+1. But they can be an extra dimension out there, a dimension of space. And there can be some being there, or some Cooper-like form in there, in that extra dimension, which is not visible to us, is not even along the same structure as us, but it can communicate with us through gravity, through sending information gravitationally. That, in principle, could be possible. Encoding this,
and this is because gravity transcends those dimensions. Is that right?
That's right. Exactly. Gravity is the manifestation of the curvature of space-time. Gravity is space and time. So if I excite the extra dimension in a particular way, I can use that to send information through the extra dimension, and that information will be sent through gravity. So that is something technologically we can't conceive. Even conceptually, we don't know whether or not there are extra dimensions out there. But as a theoretical physicist, I can explore that possibility. That is completely scientific.
You've seen that time is represented here as a physical dimension. You have worked out that you can exert a force across space-time.
Gravity. To send a message.
Affirmative.
Gravity can cross the dimensions, including time.
Apparently.
And so is there a certain type of theoretical physics that just explores these extra potential dimensions?
Yes, absolutely. So we do work with extra dimensions all the time, almost. So they used to be a bit more popular in 20 years ago, because at the time we had fewer tests on how large those extra dimensions would be. So we had potential for those extra dimensions to be not too small. But even nowadays, a lot of the things that we do, they can accept the existence of extra dimensions. Some extra dimensions where there could be other information out there, and that information could be communicated to us through gravity. That in some sense, it is possible. We can think of the whole evolution of our universe as a motion of a sort of a surface, a membrane along an extra dimension. And so what we perceive as being an evolution in time is actually the evolution of this surface as he moves along his journey through the extra dimension. So we can explore those possibilities. Those are not completely to the realm of fiction.
Very interesting. Thank you so much for that. Okay, so Kip Thorne worked on this film, and then a few years later, he was awarded the Nobel Prize for Physics, along with Rainer Weiss and Barry Barish, for contributions to the LIGO detector and the observation of gravitational waves. Now, from 2014 to now, can you do a really easy overview of what kind of discoveries have been in the world of gravity and theoretical physics?
So the direct detection of gravitational waves has just been amazing, really outstanding. And you have to think of it as really an ability now to see through a different set of eyes. We used to seeing everything around us through light. The detection of gravitational waves is very much a way to almost communicate with the rest of the universe, thanks to a new channel, which is not light. It is those gravitational waves. In my book, I call them glide because they are, in some sense, very similar to light, but they are of gravity. So there has been the direct
Can you
detection.
explain how they're similar?
Yeah, so gravitational waves are very similar to light in the sense that we can think of light. What light is a wave coming, for instance, from the sun or from a light bulb. It is a wave which are excitations in an electromagnetic fields, which travels at a specific speed. It travels at the speed of light to us. And it corresponds to really excitations, to fluctuations in that field. This is light. We're used to that. For gravitational waves, they're very similar, but rather than being excitations in an electromagnetic field, they are excitations in a gravitational field. What we mean by that, they are actually distortion of space and time. And so what we know since the direct detection of gravitational waves, we've been anticipating that for a century almost. But what we know is that when you have very massive objects, as they merge around each other, as they're about to merge, as they rotate around each other, they distort the curvature of space-time so much that it creates distortion of the waves of distortion of space-time. And those are gravitational waves, and they propagate through space and time. And we have observed them here. What we have observed is this distortion of space as the gravitational wave passes through the Earth. That is just amazing. It's just beautiful.
That is amazing. Can you explain, like, light is, for me, far easier to understand because I can see light. And I feel gravity in the sense that I'm sitting down and not floating around right now. But how do you detect that? It's not, like, because we have eyes, it just feels so much easier.
That's right. If we had cells buds for gravity, then
exactly.
So unfortunately, it's hard to detect it with our own body. Our body is not very attuned to that, very sadly so. But the way to detect that is to measure how space gets distorted as gravitational waves pass through. So the passing of gravitational waves leads to a distortion of space. A distortion of space and time. And so in practice...
And is that visual? Like, do we see that rather than... Like, is there some other... Okay, so we do... Is it that we see it?
Yes. So we don't see it with our own eyes because the distortion is actually very small. But in some sense, yes, we see it. We actually see it precisely because we see it through light. We use light to measure the distance between 2 points. That's the best way to measure distances thanks to light in the vacuum, in vacuum chambers. So there are interferometers. LIGO is a set of interferometers. There's two of them in the US. And what they have is a cavity chamber. It's a tunnel underground, which is in the vacuum. And they have two mirrors on each side, and light is propagating between those two mirrors. And as the gravitational wave passes through, you see that light takes a little bit more time or a little bit less time to reflect between those two mirrors. And it does so differently along different directions. And it is exactly this slight, very subtle, very, very subtle and small shift in how much time light is taking to connect those two mirrors that we see the passing of gravitational waves.
And I think you mentioned that there is a new detector that's coming on the scene. Is this in space that you mentioned?
Yes,
so there will be.
Yes. So there will be. So actually, you were mentioning the what has happened in the past 10 years.
Sorry.
So indeed, there's lots of exciting things beyond the direct detection of gravitational waves from LIGO that have happened. There's thanks to those detections, and then there's now some interferometers which are Virgo in Europe, hopefully very soon in India as well. And hopefully that has been approved. Actually, there will be one in space, the LISA interferometer in space, which will allow us to measure gravitational waves at much longer wavelengths. So the gravitational waves that we have observed with LIGO, the wavelength is of the order of the kilometer, about 4 kilometers or so. Mm-hmm. But for those in space, because you can probe much larger distances, They could be millions of kilometers.
Wow.
So these would be huge. So this is very
and
exciting.
This one in space,
yeah,
it is very exciting. But this one in space, sorry if I'm asking really stupid questions, but is it going to be huge, or it just has the capability to register a bigger space?
Both. So it has a capacity to it has a capacity to reduce a much bigger space. That's absolutely true. So we can see much further away with it, so we can see much more with it, but also because it probes much longer wavelengths of gravitational waves, we can see things that we wouldn't be able to see with interferometers on Earth. Something else that has happened since 2014 is almost the visualization, or what has happened since 2014 in addition, just a few years ago, actually, is the observation of what we call the shadows of black hole. So, of course, black holes are black. We can't really see them. And as light goes in a black hole, it never comes back. But if you think you have a black hole, and you imagine you have stars or light behind the black hole, then that light from behind the black hole, as along its line of sight, will be distorted by the black hole itself. And when Interstellar came out, the picture of Gargantua were actually numerical simulation made by Kip Thorne and his team to predict how light would be distorted and what we would see from a black hole, from a supermassive black hole. But actually, since then, it has been observed.
That's amazing.
It's amazing. You can
look
at
it's the same?
It's very similar. It's incredible. So you can look at pictures from Interstellar and current similar pictures, which are real observations. Not the light is not invisible light. It's some different frequency, but still you can see it, and it's very similar. So that's another way to that there has been a confirmation of the existence of a black hole at the center of a galaxy, for instance.
Brilliant, thank you. Anything else that's new and exciting in the world of gravity?
I think those are the main two things, I think.
Can you talk a bit about your own fascination with gravity? Because your book is titled, A Life in Pursuit of Gravity. Did it start at a very young age?
Oh, so yeah, it started at a very young age, and I think perhaps to start with, it wasn't entirely clear it was about gravity. It was much more about the O's of the unknown and what connects us all together. But as time went on, and also writing the book, it became clear that it was all about gravity. And to me, gravity is just absolutely fascinating because it's this overarching miracle. It's this thing that connects everyone in the universe. It is the very structure of space and time. So you can't imagine anything more fundamental than that in itself. Of course, it has all of these mind-blowing consequences that touch the realm of science fiction. But a lot of it is real as well. And it just blows our mind in how rich it is, how creative it is. But another aspect which I found fascinating with gravity is its universal nature. It's not only what keeps us grounded here on Earth, it's also what connects everything in the universe. So we can use gravity not only to describe the universe, we can use gravity to describe bulk being beyond the universe that we can even observe in some extra dimensions. That is, I can't imagine anything more fundamental than that. It's really, it's really quintessential in itself.
And your experience then of watching Interstellar, so you've just had a baby, there's this really emotional stuff with all, Cooper and Mirth throughout. And then you're being fed, I can't even imagine what it's like to watch it as you, because it must have added such an extra dimension, because you're probably watching it going, yep, that works.
Yes.
Is it really, how, does it feel quite a personal film to you?
Absolutely. I think it's one of those movies where it's gone so much in the details, and a lot of the things are actually very physical. They're actually real. Of course, you need to make a little bit more to the story. So towards the end, particularly, you have some elements where you have to accept that it's there for entertainment rather than scientific reasons. But I think it's beautifully explained, and a lot of the visual, a lot of the the science that goes through is actually real science. And what I love is it's actually a lot of the way we think about things. It's not completely out there. It's not trying too much to stereotypes what scientists are like either. There's a lot of scientific process, a scientific journey going into trying to explore and trying to very much reach some better understanding of what's going on.
I absolutely love the film myself. And I think it works on so many different levels. It works on the scientific level. And then it also talks about, how we try and identify ourselves. So yeah, I agree with you that it's a very powerful film. Okay, so thank you so much for coming on. And
thank you.
I'm so grateful for you to come and share this kind of passion you have for Interstellar.
Thank you. Thanks, Aisha. Yeah, thanks a lot.
That's it for this episode. If you do have time, please think about leaving a rating or a review for the podcast. Thank you to every single one of you who has already done that. I don't always find the reviews straight away, but when I do, it's absolutely lovely. So thank you so much. Check the show notes for which film we are covering next, and I'll see you again next time. Bye-bye.
Don't let me leave, Murph.